Hi, so this is going to be our last video of the semester. This is going to be about a presentation of the overview of what we covered in the class since the beginning. The objective of this is for you to have some material that is going to hint as to what are the questions that you may expect for the final examination, basically giving you some guide to follow in order to know what to review for the exam, which I will be also talking about during this video. So let's go here. So here's a web page. I have made some updates lately. I sent you an email this morning giving you some of the updates I made, pointing out to some of the updates I made in the past days and this week. Notably, there was a set of slides for exercises, which I'm going to talk about during this, refer to during these, this video. There was also a video explaining how to do the exercises. There was also the schedule and the Zoom room for the project demonstration number 4 has been posted here. So please go to the schedule in order to register for your time slot for the presentation of assignment number 4. I also created a video and a handout for the grading sheet and the procedure for the final project demonstration. So the handout is here and the accompanying video is here. So there is also the home examination. I provided a sample examination here. So this is just an examination or sample questions I have given in the past. Of course, it's not going to be the same question for this semester, just giving you an idea or something to practice with if you want to study or when you want to study for your final examination. So if we go to the slides now, so let's go from the start. So this is a review of the material that we've covered since the beginning. And also it's going to be talking about the final examination. So you might ask yourself, why is there a final examination in this course? It's already a lot of work, which I agree to for the project. The objective of the examination is essentially to make sure that even though you might be doing a good job in your project, one of the objectives of the course is that you master the theoretical aspects of the job of compiler design or compiler construction. So basically the exam is going to be to make sure that you are aware of this theory. So especially exceptionally for this semester, this is going to be a home exam. So essentially this exam is going to be made available on the website at a certain time, as I'm saying here. At 1 p.m. on April 29. The exam is going to be posted on the website. I'm going to send an email to everybody when it's going to be up with some instructions as to how to fill in the examination and how to submit the evaluation, the examination. You will have 24 hours from the time the exam has been posted to actually post your answer, which or to submit your answer, which will have to be submitted on the electronic assignment submission system of the faculty, which is the same system that you use to submit your assignments for the course. As this is a home exam, then obviously you are allowed to use any material you may have access to. There's not going to be any control as to what you used as sources, but the point is that I will be expecting every time you answer a question that you will going to tell me what sources did you use to actually provide your answer. And this is going to be mandatory that you provide your sources. Of course, I don't allow you to actually share answers in any way with the other students. So when I'm going to have, when I'm going to be doing the grading, I'm going to look whether or not your answers are strangely resembling the answers by other students. Of course, if you're using tools to submit your answer, then they certainly should look alike. But let's put it this way, I'm going to be looking for plagiarism. If I find that there is some plagiarism happening, then I'm going to have to report it. So please be very careful about that. So let's go to, so that's it about the exam. When I'm going to send the exam, I'm going to send instructions as to how to fill in the exam and so on and so forth. So let's go with the review. So the first thing that we covered in the first lecture, the introductory lecture, one of the things was the architecture of a compiler. So we covered that there are different phases in the compiler the construction of a compiler or the operation of a compiler. First, a lexical analysis, syntactic analysis, semantic analysis, code optimization, and code generation. So these are generally separated into a back end and a front end. The front end being machine independent and the back end being machine dependent. So I'm not going to go here. It's very important to understand. I'm not going to go into all the details. I'm not going to repeat all the lectures in this lecture here. I'm just pointing out the things that it is likely that I'm going to ask you a question on for the examination. So there are different advantages to having a front end and a back end. So it's important to understand these reasons why you may want to have a separation between front end and back end. This is essentially modularity and reusability and retargetability of the compiler. We also covered different kinds of intermediate representations. The more intermediate representations you have, the more flexibility and modularity it might give to your compiler. It also gives more opportunity for more either high level or lower level optimization steps. Normally, that's the advantage of having an intermediate representation. It allows you to have more flexibility in terms of how the different phases are being run, the opportunity to have, first of all, easy implementation of different phases, as well as optimization phases. So what are the main mechanisms that are used in a compiler? Notion of parsing tables. So that's one of the most typical questions that you certainly will have in the final exam. I'm going to come back to these things later when we cover the specific details of these. Then you also have this notion of symbol tables, notion of semantic actions and semantic records, and migration of these semantic records, which is called attribute migration. Tree traversal is another mechanism that's being used, and visitor pattern, as we saw in past lectures, is a very, very good way to actually organize a compiler starting after the parsing. Once you have an abstract syntax tree, then you can actually have your visitor pattern to actually traverse the tree and then trigger some of your semantic actions somehow automatically, and to be able to separate your different phases into different visitors that you trigger in a certain order later on. So visitor pattern is it's not a mandatory thing that you must do to implement a compiler, but it's an extremely effective tool to implement the later phases of the compiler after the parsing and generation of an abstract syntax tree. As we covered each of the different phases, we discussed in the beginning of the lecture the functioning and the role of each phase, of each of the components, of each of the mechanisms. So it's important to review these and be able to quickly answer questions about these. Okay. That's, you know, you will have 24 hours to answer the questions. So it's going to give you much more time to browse through the notes and so on, compared to if it would be a written exam and you would have 3 hours and that would be a closed book. Okay. There's also the fact that some of the phases are optional. So for example, any optimization phase is optional. If you use intermediate representation, this might be a phase that is also optional. You don't need to have intermediate representations or an abstract syntax tree. You don't need to have it. If you use syntax-directed translation, you can actually do everything in one phase. There are some things that require more than one phase. It's possible to do more than one phase, even if you're using syntax-directed translation, but it's a bit more tricky. So there are some phases that may be optional. So this is the overall view of what are all the phases of a compiler. Essentially, you start with the source code of your input program, and then you come up at the end with target code, which might have been optimized. So then you have lexical analysis, in which you translate the source code, which is essentially a stream of characters. So you transform this stream of characters and you transform it into a token stream. Then the syntax analyzer or the syntactic analyzer or the parser basically takes this stream of tokens and then determines if it's a valid stream of tokens according to the grammar that it encodes, that is encoded inside of the parser, or that has been used to actually generate the parser. And then the syntax analyzer determines if this is a valid program. If it's not, it would tell the user what are the factors or what are the syntax errors in this program, what are the factors that makes it syntactically invalid. And if it is valid, then would output a syntax tree. Even if it is invalid, if the program is invalid, it should still output a syntax tree. Of course, the more it is invalid, the more likely that the syntax tree will be broken, or there's going to be missing parts in the tree, which may result in other errors later on, of course. But it should always be able to output a syntax tree so that the further stages, especially the semantic analysis phase, should be able to proceed even though there was syntax errors. So after you have a tree, like an abstract syntax tree, by the way, even if you don't have an abstract syntax tree, the result of the parsing process is always that you are constructing some kind of syntax tree. Even if you're not building an AST, the operation of your parser is somehow following an abstract syntax tree, even if it's not building it concretely. So you always have a syntax tree that is being produced, or at least traced somehow by the operation of the parser. So let's say you would have a tree that you construct. So what the semantic analysis does is that it basically traverses this tree and does annotations on this tree. So for example, would assemble information as to, let's say there is a class. It would identify what are the members of this class, whether these members, for example, are an array or an object. So it basically is gathering or aggregating some information finding larger building blocks by aggregation, and then eventually would build the semantic information of the program. So what's the nature of all the identifiers that were defined? What's the type of an identifier that is associated with an identifier? Is this type used to define an array or a multidimensional array? Are you defining an ID, which is a class which aggregates many members? When you define an ID, which is a function, what are the parameters of this function? What is the signature of this function? Or inside of the function, there should be, or there very often are, some variables that are defined or declared inside of this function. So you actually define all the variables that are defined in the function, which allows you later, for example, to create a stack frame for this function at runtime. So this is all information gathering that you do as you do the semantic analysis, and you basically annotate your tree with this aggregated information that you gather as you traverse the tree. So that's why it's called an annotated tree. For example, as you do semantic analysis, you are creating your symbol tables, and these symbol tables are somehow linked with the nodes inside of the tree. So your tree become an annotated tree, or sometimes you say a decorated tree. Then, once you have this annotated tree, that's basically you have a semantic tree, the abstract syntax tree, in which you have some aggregated semantic information that is has been added to different nodes in the tree. Then, once you have this tree, you can actually do some high-level optimization. Optionally, you don't have to do that, but once you have the tree, you can somehow traverse the tree and analyze it and figure out if, for example, there might be two different parts of the tree which are the same, in which case you may want to merge these two branches of the tree, so on and so forth. So lots of different kinds of high-level optimizations can be done. We did not cover much optimization in this course, as you know. That doesn't mean it's trivial. That doesn't mean it's limited. There's actually a lot of different kind of optimizations to be done, so much so that I basically chose to not even talk about it in this course. You could have an entire course about all different kinds of optimizations, high level and low level, that could be done on a compiler. Then once you've done the optimization, then you come up with, you can come up with intermediate code, which is also, as the intermediate result of the AST, is something that is, you don't necessarily have to have it. We've covered in the, one of the lectures before, we talked about code generation. What is intermediate code? I'll come back to that later in this lecture. Then once you have this intermediate code, then you can proceed with target code generation. So in our case, that was moon code generation. So depending on what, if you have a Java compiler, it's going to be bytecode generation. If you have a C compiler, it's going to be machine code generation. Then even when you have your target code, then you can actually optimize this code. That would be very low-level optimization. For example, let's say you're generating machine code. Then if you are generating code for a machine that has multiple processors, then you can actually then make it so that this code can, separate, can be executed somehow in parallel into onto the different processors that are available to this particular computer on which you are, for which you are generating the code. These will be low-level optimization. This is just one example. Again, we did not cover this in the class, in this course. Okay, so let's be more specific here about all the phases. again, here, gonna go somehow quickly over all of these. So lexical analysis. So what is the roles of lexical analysis? First, you remove the white spaces, process the comments, eliminate the comments, check and recover from lexical errors. There's very few kinds of lexical errors. And the main goal of the lexical error is to create, to transform this stream of characters into a stream of tokens. How is this organized? How is this designed? So it's always about transforming your lexical specifications into some kind of DFA. Okay, even if you implement it manually, it's always good to think of it as a DFA and have this DFA to drive your coding process. In real life, you'd actually always use a lexical analyzer generator. And the lexical analyzer generator, what it does is basically it implements the sequence of actions, which is the for transformations, which is first Thompson construction and then Rabin-Scott power set construction. So you would feed it a regular expression or a set of regular expressions, and it generates an NDFA, and then from the NDFA generates a DFA using Rabin-Scott power set construction. So that's how it's done in real life. Independently of how you do it, even if you code it manually, always the best idea is to come up with the DFA and then guide your coding from the DFA. So for implementation, you can do it manually. You can do it using a case statement, or you can do it manually using a manual implementation of a DFA. In real life, you would actually be using a lexical analyzer generator, such as Lex, for example. So notable examination questions. First, generate a regular expression out of lexical specifications, generate an NDFA using Thompson's construction from the regular expression, and generate an NDFA using Rabin-Scott power set construction from, generate a DFA from the NDFA using Rabin-Scott power set construction. This, there's actually two exercises like this in the slide set for exercises. It's actually the same questions as I'm pointing out here. Next step is the syntactical analysis or parsing. What are the roles of parsing? Here you analyze the program structure. So you have the syntactical structure of the program. How is a valid program? What's the syntax of a valid program? So you normally it's provided to you as a grammar expressed in some kind of BNF, and then you somehow use these rules and you follow a certain procedure to actually hopefully automatically generate the parser. Another role, very important role of the syntax analyzer is to check, report, and recover from syntax errors. So error reporting, error checking, and error recovery are one of the central aspects of the syntactical analyzer. So you want it to be able to report accurately hopefully all the errors, not always possible. But even if there are some errors, it should be able to continue and recover so that, as I hinted at before, so that a following phase, which is the semantic analysis, can somehow proceed. Of course, the more errors you have and the more significant are the errors, the more it is possible that it's going to lead to the semantic analysis to report errors which are due to the syntax errors, or the fact that the syntax analysis syntactic analyzer might not be able to recover very efficiently. So about the design aspects of parsing, it's always, not always, but vast majority of cases, methods are based on a generative context-free grammars. So this is basically what it's doing, is that it's trying to generate a derivation. So that the notion of derivation is a central aspect of almost all parsing methods. A very important concept to understand. As I will hint out after, very likely that in the exam you're going to be asked to write a derivation given a certain grammar and given a certain phrase and input. So this derivation is actually some kind of formal proof proving the validity of an input program according to the grammar defining the language. So essentially a parser is some kind of proof system that allows you to check or prove whether a series of tokens is valid according to the rules of a grammar. Okay. And the derivation is essentially the proof that proves or not, or disproves that this series of tokens is valid or invalid according to the grammar. All parsing methods, again, I'm saying all here, not necessarily absolutely true, but I'm saying here that in the vast majority of cases, parsers are using this notion of first and follow sets. So very important that you understand this. Again, very likely question in the exam. Giving you a grammar, generate first and follow sets. Sometimes you also have to do grammar transformation. Especially if you're using, as we top-down parsing, which forced us to actually transform the grammar into an LL1 grammar. So in which case we had to remove left recursions. If there are some ambiguities in the grammar, we had to remove them. So often grammar transformation is an important aspect of compiler design, if you want, especially if you want to use top-down LL1 parser. That's actually why the LR methods are most often used. All designs are based on a stack mechanism. You might argue somehow that the recursive descent predictive parser does not use a stack, but if you think about it, it actually uses functions which are themselves stored in the execution languages stack. So it actually uses this stack as the stack mechanism for the operation of the parser, as we saw in class. If you remember, I spent some time every time I was explaining the table-driven LL1 parser, our predictive parser, spend some time to explain to you how it does. It actually seems to be very different because it is using a stack, whereas there is apparently no stack in the operation of the recursive descent predictive parser. But if you think about it, it is actually using the function called stack of the language you're using for the implementation. So in the end, they're all using some kind of stack. So for top-down methods, you have predictive parsing, which includes recursive descent predictive parsing, table-driven table-driven top-down parsing. So these require very often a substantial amount of grammatical transformation, or transformation of the grammar to remove left recursions, ambiguities, and so on. Then you have the bottom-up methods. In the class, we covered SLR and CLR and LALR. These are all using the notion of items generation of item sets that are that's a set of item for every of the states in a DFA that represents the operation or the moving forward in the processing of the parser. All the parsers are using this notion of synchronizing tokens for error recovery. So as you encounter an error, what you are essentially doing is if you are parsing a certain right-hand side, and then you encounter a certain token, and this token that you see does not fit with the definition of the right-hand side you're currently parsing, then you have two options. So first, you have to get rid of this token which does not fit with your grammatical definition. So basically, you have two choices. You skip tokens until you encounter something you are expecting, or in some cases, you might actually say, okay, I'm going to forget about this rule I was using, and I'm going to remove it from the stack. Okay, so these are the two options. And no matter two options you are choosing, it's always defined using this synchronization tokens. And as we saw in class, it's always, or it can be based on the first and follow sets. Okay, so this notion of synchronizing tokens is also very important for error recovery, which is a very important aspect of syntactical analysis. Then you can have also abstract syntax tree generation as an intermediate representation. All compilers are actually using an abstract syntax tree because it makes possible later on to have many different phases. An industrial compiler will have eventually dozens of different phases that are implemented after the parsing has been done. If that's so, then you actually absolutely need to have some kind of abstract representation, most of which are using an abstract syntax tree or some related data structure, as we saw in class. Then you also have this notion of attribute migration and the semantic stack, which we saw in the top-down methods, the table-driven top-down method, which was using a semantic stack. This notion also of attribute migration becomes very important if you had to change your grammar, for example, like removing left recursion and so on. Attribute migration can become much more of a problem, you might say, a problem you have to solve because of this notion of the inherited attributes, which are introduced by this very often by the transformations you might apply on the grammar. So it's also an important thing to review for the exam. Then for the implementation of syntax analyzers, again here I'm going to only cover what we saw in class. Okay, there might be other things. Of course, there are other parsing techniques. What I'm reviewing here is only what we covered in class. Okay. What we saw in class is recursive descent, top-down parsing, table-driven top-down parsing. For the bottom-up methods, we covered SLR, CLR, and LALR. Okay. For example, for the bottom-up methods we covered, it's basically generating a state transition table. This state transition table contains two parts, an action part and a go-to part. This is often called a shift to reduce parser. Invite you to review what's the meaning of shift, what's the meaning of reduce, and so on, and what's the definition that we use in this mechanism. So what kind of questions can you expect for the exam? So given a grammar, generate a table for a table-driven top-down predictive parser. Given a grammar, eliminate rough recursions or ambiguities in a grammar in order to, for example, make it LL1. Another question, given a grammar and a valid sentence, provide a derivation, providing that this, proving that this sentence is derivable from the grammar. Given a grammar, generate a set of the item sets, either CLR, SLR, or LALR. Okay, again, only related to what we covered in class, which is these three bottom-up methods. There are other bottom-up methods. You're not going to be tested upon them. So generate the item sets and the states and so on, and then generate the corresponding state transition table with the action part and the go-to part and so on. And also generate the DFA that it corresponds to. For this here, and then this one here, there is, if you look at the exercises slides that I made and the accompanying video, it's going to guide you through exercises about this. The exercises slides don't show the actual, all the steps involved in finding the solution. If you want to see the steps involved, I remind you that there are on the slides for the lectures, there is an example showing all the steps involved. If I'm asking you, I will be asking you questions like this, I'm going to expect that you provide not only the answer, but that you provide the steps involved in finding the answer. And finally, given the state transition table and a token stream, execute a parse trace. Again, we've had this as examples as I was explaining these parsing methods. You should also look at the example, the sample exam that I posted on the course webpage. There is an example of questions like this and the kind of answer I'm looking for. Moving forward, and then you have semantic analysis and translation. So this is basically where you continue further after you have the abstract syntax tree. You'll basically aggregate some information, construct symbol tables, and eventually translate this program into an executable. So these are both things that are often grouped together because it's about semantics. It's about finding a possible meaning to this program that you have successfully parsed, for example, finding what can be the meaning of this program, and if it has a meaning, then how to translate the meaning of this program into an equivalent lower level meaning that the actual computer can execute. Okay. So semantic analysis and translation is about finding the meaning of a program, and if it is, it's about translating an equivalent meaning that the program, that the computer can execute. So what are the roles of this phase? Verify the semantic validity of the program to determine if there can be a meaning to this program. It's possible that the program can be syntactically valid, but it's semantically invalid. For example, if it's referring to a function that does not exist, it is syntactically valid, but it's not semantically valid. And then if it is valid, then you can actually translate it or find an equivalent program written in a lower level programming language that is understandable by the computer that you then feed to the computer to execute your program. How is this organized? Concepts in the design of semantic analysis and translation. Notion of symbol table, absolutely central to the whole operation of both the analysis and the translation, as we saw in assignment 3 and 4. Then you may have intermediate representations and intermediate code. It's much easier to do these phases, these two phases, if you have some kind of abstract syntax tree, so that you can do several phases, one after the other. And if you want to have the opportunity to optimize your output code, it's better to actually come up with some kind of lower level abstract representation of your translated program upon which you can do some analysis and optimization. So very often you would have in this semantic analysis optimization phases, either at high level or at a lower level. The notion of semantic actions is central to this whole thing, to this whole semantic analysis and eventually translation. And you have this notion of semantic records, which are basically data accumulators that you use to aggregate some information together to create higher level building blocks of information that are associated with a higher level abstract syntactical constructs. So for example, a data structure declaration or a class declaration or a function declaration, these are all higher level syntactical constructs, and you want to accumulate some information that contribute to their definition or declaration. And you would use semantic actions to aggregate this information, and then you would aggregate this information in semantic records. So very often you would actually do abstract syntax tree traversal and optionally be using the visitor design pattern. Again, I can't emphasize enough how visitor pattern is a wonderful tool to organize in a very orderly manner and efficient manner these steps. So about the implementation, so you organize this in the part of way you organize this information is using symbol tables. So you might have nested tables. For example, if you define a class has data members and member functions. A member function can itself have a corresponding symbol table. So in this case, you would have the class table that contains the tables for each of the member functions of this class. You have other languages for which it is possible, for example, to have an inner class, which would be a table inside of a class table. Other kinds of languages also have a possibility to have inner functions. You define or declare a function inside of a function. So in this way, you have, imbricated symbol tables. So symbol tables are very often nested. And one of the goals or uses of a symbol table is to manage the notion of a scope of a certain syntactical construct, and to separate the scoping so that you can have some variables that use the same names but in different scopes, for example. For intermediate representations, you can have trees, or most appropriately directed acyclic graphs. Then you use tree traversal or tree analysis algorithms for further processing stages. Then you can also have intermediate code if you want to output code that is expressed in some kind of abstract yet lower level way. You can actually output intermediate code, which allows you to do some further analysis, but lower level analysis. So the more you have intermediate representations, which are some kind of abstract representations, the more it allows you to do more reasoning about your output and possibly to optimize your output. Notable examination questions. Given a program, sketch its corresponding symbol table structure. Given a simple statement or expression, write the corresponding Moon code translation. If I'm asking you to write Moon code, it's going to be about a simple program. I'm not going to give you a sizable program and then ask you to write the Moon code. As you probably saw in assignment number 4, very quickly, if you start having, for example, some expressions inside of your statements and so on, the code very easily grows larger. Okay, if I'm asking you a question about writing Moon code, basically I'm giving you a simple question and then I want to see if you know your Moon code. That's what I want to see. It's not about writing the entire code for a somehow complex program. So that's it for that. So here are some references. Of course, you should, the objective of this is that you review the material we saw in class. So here I'm giving you some references to books. That doesn't mean that you have to read these books in order to study for the exam. However, it might be that as you read my slides, you ask yourself a question. Maybe this question, you can find the answer inside of the books, but never will I ask you a question for which you cannot find the answer in my slides. Okay, that's what I do in all my courses. Always asking questions only about things we discussed in class, which is all written in my slides. So the main material that you have to review for studying for the exam is the lecture slides, as well as the exercise slides. So what I mean by that, exercise slides, these are the slides that you will find here. Okay, I invite you, if you did not see that yet, I invite you to look at the video I did to explain these slides. It's basically exercises about how to use tools to find, online tools to actually find answers to questions as from a regular expression, generate a NDFA and a DFA, or for parsing, given a certain grammar, generate a SLR, CLR, or LELR table, or an LL1 table, okay? So it's basically some exercises that I gave. There's also some examples that I gave in almost all the lectures. For example, for the parsing, when I explained SLR, then I gave an example in the slides as to how to use the SLR method to construct an SLR table. So these are sources that you can use to actually figure out how to answer the questions to the exam. So all this to say that if you want to study the exam, study the slides I just given you in this very video. That gives you pointers as to what are the likely questions. That basically tells you where you should concentrate your studies. Look at the exercises here. Make sure that you know how to use the tools I'm proposing in the exercises. I'm not going to expect that you use exactly these tools, but you know, that's the tools I found that were the best. You may find other tools for sure. If you find that they are better or that you're more at ease with other tools that can give you the same answers as the tools I'm proposing here, go ahead. But if you, whatever tool you use, either tools I'm showing you here, I'm proposing to you, or if you use your own tools, you have, when you provide your answer, you have to mention or give the URL of what is the tool that you used, or any other source that you use to actually provide an answer. You have to give it to me as part of your answer. Finally, the other source for helping you study for the examination is the sample examination I gave to you here. So I invite you to look at this exam, look at the questions, maybe try to answer the questions without looking at the answers, or maybe you want to look at the answers right away. I don't know, but here you have some examples of questions that you may expect for the examination. So that's it for this video. So see you around. Bye.